This is an 80s inspired game I called Miami Race. I made it in Resolve. I mean, I am playing it right now in Resolve using this joystick. Like most 80s console games, Miami Race overpromises in the opening screen and underdelivers in the gameplay. But as a kid, I was excited about far less refined games than Miami Race. How is this even possible, right? Resolve is not Unity nor Unreal. Well, we'll get to that soon. Hi, and thanks for joining in. I'm Igor Reginovic. I first covered the Resolve API scripting 4 years ago in several YouTube tutorials, but since then I've been busy writing actual Resolve API-based tools for Metafy.com and for products like ColorLab AI, and I haven't had time to make new scripting tutorials. What's really behind this crude game is that I wanted to introduce you to using hardware controllers like a joystick, which normally you can't use with Resolve straight out of the box, and using it for far more useful things in Resolve. And we'll actually cover that in part 2 of this 2-part tutorial, where I'll show you a joystick-based pan and scan setup for reformatting conventional aspect ratios for social content videos. But what we'll do first here is I'll show you what you're probably dying to see. How the heck is this possible? Let's take apart Miami Race. You can see that all of the gameplay's action takes place in the edit page. You can think of the game as having 2 independent visual elements, the animated background and the foreground car. With the small exception of some free 3D models and a tiny bit of modeling in Blender, most of this is all pure Resolve infusion. I have initially built this racetrack and animated the camera to run in a smooth loop, only to discover that you can't translate and zoom an edit page layer while the playhead is running. See how I can change the X value of the car layer, but the car won't move until I stop the playback. Because of this, the background animation needed a different solution and a more complex one. My game timeline is only 1 frame long and it consists of 51 layers. See how when I run this Python script called cycle, the layers start muting and unmuting in succession. Each layer has 1 frame of the racetrack animation. We're essentially frame cycling the 50 layers. The 51st layer is the foreground car, which is always turned on. This gives us a strobe illusion of movement. The 50 frames we have here, that's not much. I could have probably gone with more, but I'm really focused on the joystick thing here, not so much the background, so I didn't really care. One thing I had to do was to shorten my original racetrack because running the entire length in only 50 frames would have made the animation really fast. This new track design is kind of simple and repetitive with only a handful of curves. When the camera arrives at the end of the track on the frame 50, it's aligned to create a sort of a seamless loop with the frame 1. I rendered that. See how the camera animation loops? Although you can still see a little jump at the seam. I cut each frame onto its own video track. Let me show you real quick how the muting works here in a timeline with a single track. We'll go to Workspace menu to open the console. I'll switch to Python 3. With any scripting, you have to build some basic objects first. What we really need is an instance of the current timeline. To get to it, we first have to instantiate the project manager. Then the current project. And from it, we get the current timeline. Once we have the timeline instance that I called current timeline, we can mute track 1 like this. Current timeline, set track enable, video 1 false. Or we can unmute it with true. This is how the cycle.py script works. We have an infinite loop cycling through the 50 track index positions and selectively turning them on and off with some strategic time delay in place. Now, the foreground element is the one I'm more excited about. There's another Python script I named controller, which reads the joystick input and applies it to the layer 51, which is the car. The API has no way of reading external controllers. For that, we're using Pygame, which is a third-party Python game development library. But let that not confuse you. We are only using Pygame to read the joystick values. Everything else is handled by Resolve. Applying those values to the layer is the fun part. Let me demonstrate that. While we still have a valid current timeline instance, I will add the card to track 2 and get an instance of that timeline item by calling getCurrentVideoItem on the current timeline. Now with the instance of the video item, we can read and write some of the properties of this item that are normally accessible in the inspector panel in the edit page. Let's read first with get property. You can see how the property values shown in the console match those in the inspector, although the labels may be a little different. Now let's move the car to the right by 100 pixels. For that, we use set property and use a dictionary as an argument. So we'll say car set property pan colon 100. See, it jumped to the right. Now let's move the car up and also change the opacity to 30%. Tilt 110, opacity 30. You get the idea. Now let's look at the controller.py script that we use in the game. At the top of the script, we do the same Resolve instances building like we did in the console earlier. We called our timeline item instance car earlier, but here I'm calling it current video item. Then we do a canonical Pygame joystick initiation. We scroll down to the bottom and see we're calling the main loop, which is an infinite loop. At the top of the function, we set the values for the size and position of the car because it's too large to fit the roadway, and then we enter the loop. See, we have these pan, tilt, and zoom variables. They hold the values we sent to the car item at each pass of the loop using the set property method, which we already know how it works. See here. The only new thing is the zoom gang, which locks the X and Y zoom parameters together. Let's go back to the top of the function again. Here we reset the car position if the player presses button 1 of the joystick. Here we read joystick axis 0 and 1 and store them in these two variables. We use these two variables to calculate the values for our pan, tilt, and zoom. Why is this necessary? Because the joystick reports axis values as normalized positive and negative values, which means that our pan and tilt would only move by 1 pixel per loop cycle, which is too slow. How did I arrive at these formulas? By pure trial and error. You can also see how zoom is dependent on the tilt value because we want the illusion that the car is speeding down the road. So when we push the joystick down, the car becomes smaller. And when we pull the joystick back, it comes closer to the camera. With the pan, tilt, and zoom in hand, we have all that we need to push to the car item, but we also want to set the limits to make sure the car is confined within a certain region of the screen and never leaves the frame. And that's done by the block of code here. The clock tick is a Pygame way to set the refresh rate. I believe this means we're running at 60 loops per second. Here at the end, we set button 6 to quit the game. It's not strictly necessary when running the script externally like I do here, but if you ran it from Resolve's script drop-down menu, you'd have no way of breaking the loop without something like this. Normally, I'd combine the controller loop and the frame cycle loop in one script and run them in multiple threads, but I was running into issues maybe because of the Pygame loop, or I'm not sure why. Instead of doing that, I launched the two scripts with this batch file. You could write an equivalent startup script for macOS or Linux in Bash or whatever shell you're using. One final note up here, for external scripting, I use my own method of loading the API library, but you can also use the technique that's provided by Blackmagic in the sample scripts. And if you're running scripts internally, which you have to do for the free version of Resolve, then you don't even need these two lines because the Resolve instance is conveniently provided for you. Make sure to catch part 2, where I show you how to build a pan and scan setup with a joystick. Thank you for watching this Resolve scripting tutorial. I'm Igor Rijinovic, and you can get some of my software tools at metafight.com, where the free computer vision plugin for Resolve has been very popular.